I think I have a collection at home too, just in my corner. I have I have a bunch of these telesprogs. The telescan last time gave me like 10 telesprogs, and I just put them in just sitting in the corner of my room. There's like 10 telesprogs and like all these other stuffed animals and frogs. I don't know why they chose frogs, but that was their thing.
They are into rainbows.
Okay.
Oh wow, you look 10% smarter, you know.
I get 10% smarter. One more just might show up.
We can move on. I mean, we've only got 45 minutes now, right? So. Yeah. So for those who weren't here, which was I guess just you two a moment ago, I'm going to post some more papers. So if you're interested in what papers I post, volunteer for it. Otherwise, then there's things you might want. Because I'm going to start scheduling the second half. Okay. Yeah. So let's move on.
So this paper presents ESP path sensitive program verification, presents a new approach for partial verification that runs in polynomial time and space. And so first, the definition of verification and temporal safety properties. Safety properties are a class of properties that say what should happen and what should not happen. For example, you should not close a file if you haven't opened it, or you should not release a lock if you haven't acquired it. Partial verification means verifying that program does not violate these temporal safety properties. And by the way, temporal safety properties are defined by programmer, and programmer use FSM to represent temporal safety properties. This is the FSM for open and closed behavior profile. Oh my God, I changed this. So previous works for partial verification were taking into account past insensitive analysis and past sensitive analysis. Past insensitive analysis, which is the data flow analysis, the regular data flow analysis, is inaccurate and it's not precise enough. Past sensitive analysis tracks every branch in the control flow graph, which is, so if you track all the branches, this would be exponential time and would be expensive. So if you have a large program, it's not scalable.
Why is that exponential time? I mean, if you track every branch, well, gosh, there are only so many branches in the program, right?
So 2 to the power, because there are like 2 arms for each branch, and if there are like many conditional branches, would be 2 to the power of the number of branches. So an obvious solution would be, why would we track all the branches? Why not just those that directly affect the temporal safety properties? So this paper's contribution is what I said. It presents an analysis framework that is only as past sensitive as needed to verify a property, and also includes an interprocedural version. It is also a verification system using property simulation that I will explain soon, that will scale to large programs such as VCC. Property analysis. So basically, it's either data flow analysis, which doesn't merge at the merge point. Sorry, just a second. Okay, I changed this and this has to be after that. Sorry, I forgot to get rid of the person. So what does property analysis do? At the merge point, we can choose the level of path sensitivity. Merge point, do you guys know what I mean by merge point? At merge point? So when we have a data flow graph, do you know what I meant by merge point?
What do you mean by path sensitivity, first of all?
So
With the path.
maybe draw a small diagram on the board that shows,
Actually, I would have, so this is the
well, I think if we go through just a simple example of the definition first, then it'll be clearer when you get to that example anyway. So maybe just draw a control flow graph for two if statements, one after the other.
Draw on the board.
Sure, sure.
So, for example, if we have an if statement, and if f equals to 0, if it is true or if it is false. So after this, we would have to merge to see the results. After each condition, we will merge to compare the result after the conditional to compare the states after the conditional to what it was before the conditional.
So actually draw in the merge point and have another if statement right after. And that'll help us work through what path sensitivity is.
For example, if true, then open. Then we have to merge here. Or if it false, do nothing. Here we have to merge. Because before this, we have a state that will explain the format of the state. After this, the state would change depending on the paths that we take. Path sensitivity means this path or this path. Which arms of the conditional, true or false?
So that can happen. You can track branch information like that even with normal data flow analysis, right? Even with something that's not necessarily path sensitive. So if we extend the example a little bit, it'll highlight the difference.
So you mean why the merging point?
So put another if statement after the merge. Put another if statement after the merge. Huh.
If
And it doesn't matter what the condition is, it could be anything. But then, based on this condition, maybe along one branch you read from the file or something like that, and on the other you don't. Right?
yes.
So draw that in. And I think this will.
Or actually, since we are reading the file here, maybe here I don't read the file, so you can see the difference between data flow and.
Well, what we'll be able to see if you read from the file down here is how the path determines whether or not there's an error versus just the branch.
For example, F close here.
Okay.
If we come from this path, then there would be an error.
Mhm.
We have to make sure that this would be the path that we are taking to reach this state.
Is that what's defined as path sensitivity?
Essentially, yes. Essentially. Being able to tell what paths are possible, which paths aren't. So for instance, if this condition down at the bottom is related to the condition at the top,
This is close.
then you should be able to tell that, for instance, well, if you get to F close, maybe you took the true branch up there, and so it's safe. And maybe you can never take the false branch and then continue on to take the true branch at the bottom to try and close something that was never opened. So you can analyze the path-specific behavior. And there are an exponential number of paths, like you mentioned before, right? Because every condition gives you another factor of 2. So that's why this is a challenge.
Does not the fellow the data flow analysis contains the information that we can get the grant the past sensitive analysis doesn't have any implicitly. I think it can cover.
Okay, I didn't quite hear all of the question. There's a wonderful fan behind me. I heard can't data flow and then.
Actually, I didn't understand what's the difference between data flow analysis and past sensitive.
Okay.
Oh,
Okay.
I'll explain that
Okay.
in the figure.
So. Okay.
Just for now, keep in mind that we can choose the level of past sensitivity.
I think it might be okay to even go through it in a simpler example at this point, and then we'll see it in detail in the figure.
So
But
this is not simple.
it's
This
not.
is actually comparing data flow.
It's not as simple. So I think this gets very concrete. We'll go through the details there. But if we just think at a high level, like I can ask a very simple question that I think highlights the difference. So if you look at that figure on the board, will data flow analysis tell you that there is an error at F close? Why do you say no?
Because for it, in that path is reachable, right? And it doesn't care.
Okay, but data flow analysis doesn't generally reason about the paths by default, right? What happens at the merge in traditional data flow?
So data flow is path insensitive.
Yeah.
So we would merge all the what we call symbolic states.
Right.
So
So-
basically, if there is a relation between a variable and a property state, data flow doesn't capture that because it merges everything.
So more simply, if we look at this example, and we've seen this file open example before, right? We used that in class. As soon as you hit that merge, we know that the file could either be open or not. Because along one path it was opened, on the other path it wasn't. So as soon as we merge, we know that it could either be open or not. So that means when we go down and look at the 2 branches of the if statement, well, along this branch it could either be open or not. Along the other branch it could either be open or not. And when we get to the F close, well, it could either be open or not. So conservatively, we'd say that could be an error, because if it's not open, that's an error. Right? So data flow analysis would say, we merge the analysis of the paths together. And as a result, we have to assume there's potentially an error there. A path-sensitive analysis says, I can specifically determine the behavior along each path, so that if I know that there is no valid path that took the false branch and then tried to do F close, then I know there's no error there. It can reason about the behavior of specific paths. Is that clear? Okay.
Okay, the difference is that data flow is not path sensitive, so merge all symbolic states. Path sensitive does not merge at all. At each merge point, you just add the current state to the states that you have. Property simulation, that is what the paper is doing, only merges symbolic states that are not relevant to the properties being verified. For example, if you have if here in this example, this was if f equals to 0, set x to 1, then x equals to 1. This has nothing to do to the properties that we were considering, which were files, opening and closing files. This has nothing to do with that. So the third one, which is property simulation, would lose the information about this x equals to 1. While path sensitive will have this information. So here I'm explaining just a little information about the symbolic states that I was talking about. States are carried in during the analysis in symbolic state form. They have two components: abstract state, which is basically the states mentioned in the property FSM that the programmer presents. For example, open error, and execution state, which stores the map program, which are the stores that map the program variable to variables. For example, x equals to 1 if could be an state, could be an execution state, or if x greater than x more than 0, f open x more than 0 is one execution state. Basically, whatever is related to your variable. Am I clear?
I think this part's what will become much clearer when you look at the example for property simulation.
So just keep this in mind, because now I'm going to run an example. So this was a simple program, and this is the FSM for the program. This one. So here we see the difference between, at merging between probability simulation, path sensitive, and data flow. So I'm not going to go, I don't have to go through the whole thing, right? Because it is basically repeating. Maybe
I think it would be helpful,
if I go through everything.
Probably, yeah.
So T means U stands for the basically the first value is for the property state, and the second is the execution state. And T means initial, we have started. So we start with U and T, and then if D at this node we separate, we have two paths. On the right side shows when it is false, left side is when we take the two paths. So when it is true, what happens is that the execution state changes to D, because D is true for all of them, for data flow, property simulation, and path sensitive. And at this point, the condition is opening the file, so the property states will change to open due to D being correct. So it would be open D, open D, open D.
So at that point, they all behave the same.
Yeah, all the same. And same thing for when D is not correct. When D is false, it will stay at U, initial property state. Now at the merging point, path sensitive analysis just merges the before and the after. So at the merge point, we have open and D, and U and not D. Actually, the two passes, merges the two passes. For the property simulation, we have open and D and U and not D. again, we will keep both states because they're related to the property states. We are opening and we have open and new. Data flow, because it is D and not D, changes the execution state to T and merges the two property states.
So that's not actually a T, right? Do we remember?
Means all. T means all.
Top, right,
Top.
right, yeah. So at this point,
But the-
we can see that the data flow is approximate, but the property simulation and the path sensitive are the same.
Yeah, they're the same because the property state and the execution state are related. So the execution state is affecting the property state. How about here? Okay, now here is a good example. So now here, if P is true, we have two conditions. So if P, if for the easiness, for the convenience, this is how it is showing. P, not P and D. Basically, could be separate. Could be not P, comma P. So if it is true, P, if P is true, then it would be U not D P and OPD.
What does that mean?
Sorry, just a second. Confused. Oh, it's not. It's sorry. My bad. It is P not D. So basically, we take the previous path and then we add the condition that is P is true to the previous one. Previous ones. So it would be U not D, O D would be U not D P, O D P. When P is true. And on the other side would be, again, these two paths, adding the condition that P is not true. So it would be U not P not D and O not P not D for the path sensitive analysis that keeps all the states. But for this one, we would have the same thing. We would still have U P not D, O P D, but at the merge point, at the merge point, we would lose the information about P because basically these states are not changing when P is changing. P and not P does not change the state of U and O. So that means that P is not affecting the property state. So at the merge point, we lose the information about the correlation between P and property state.
So when you're in the middle between the if P and the merge, you're in this x equals 1, x equals 0 zone. The algorithm at that point doesn't know if you can get rid of this information.
Correct.
So every path is followed, but not the data about it not kept.
Right. So you can think about it maybe as being kind of like garbage collection, where after a certain point they're saying we no longer need this information because it's not telling us anything useful, so let's throw it away.
Okay. But isn't there still exponential paths that it follows? Or is it just...
Well, so here's the thing. There are still exponential paths that you're analyzing with data flow analysis too, right?
Yeah.
So why isn't that an exponential blow up?
Because you ignore most of the information.
Because you ignore most of the information, you group paths together. So you over approximate and say, well, consider a group of paths at the same time, so you can cluster them into an abstraction. You got this group of paths you're analyzing once, and you're doing the same thing here. By throwing some information away, you're saying that that we don't need to consider something. So if we think about the execution tree, right, because we talked last time about the execution tree, there's a big relationship here where you're essentially saying that with a full execution tree, and that's how you get exponential blow-up, right? Everything would spread out and it would have a tree structure. The exploration here is no longer a tree structure because some of the paths come back together.
So, sort of deviate a little bit, but what, does that mean that loops are a lot easier with this? Because loops are, right, you still have problems. One of the issues we had last time was loops. I was just wondering how actually.
It should be. I mean, so for a couple different reasons. One, because what you're analyzing is a finite state machine, which means there are a very limited number of states that are interesting to you.
Okay.
And we'll see this when we talk about some of the complexity stuff, I think, maybe. And so that just bounds the number of things you ever consider.
Okay.
And I guess that's really what ends up being nice in the case of loops, right, as well.
And for the data flow, here we add P, but here we have not P, so when we merge again, we would reach U, open, and T. So again, we, at merge, we lost the information. Should I keep going? Like, to the end?
We can go through, just through the close, so people see what happens.
So right now we merge everything. PSA would merge all would keep all the states, these guys and these guys, which are 4 states. We have 2 states here and 1 here.
I have a question. So why doesn't the P state is being recorded in data flow?
P state is recorded in the data flow
Yeah, so just after that, like where it turned back to top,
here.
is P being still recorded or like
What happens at a merge point in data flow?
they
At
merged,
a meet?
they merged the states?
Okay, so what happens when you have P and not P?
Yeah, not the other.
Yeah, but in the curly braces there is no P, so I was confused.
There's no
That
P,
P
but
became
this
top. The
P
That P became
and, P and not P became top.
P and not P. Now at merge at okay. Now if D if true, we would again if D is true, now we have D here based on our information. If D is true, would be only these 2 guys for the PSA, and if it is false, would be these 2 guys for PSA. Here, that's a good thing that we have the information. That's why it is good to have lots of information about all the correlation between execution states and property states.
Yeah.
Here we could take the right path
Why can we do that?
because we have the correlations here
What correlations?
between D and we know the value for D.
Right, right. So we're able to tell that we're checking something that we already know the value of, so we can prove that some paths aren't possible.
Yes. And here we can also do the same thing for property simulation. Why? Because we had the correlation between property state and D before from here. So again, here we can take the right path. If it is when it is open, D is correct, so we go to the closest state, and when D is not true, we don't go to the closest state. So no errors. But if we didn't have the information about what will happen, the question is what will happen if we didn't have the correlation between D and property state. So we would reach here, and then we would check, but we don't have the information. So we could go to this state, while we could go from you to close, which is error. But because we know that when it's you, it's not D, we didn't go to close. So that's the good thing. And when we merge U, the close. After close, the state from open, the property state changes from open to U. It's a transition from open to U. And then we merge, so it's U, D, and U and not D, which is top. And here we merge all these conditions, these four. We can actually keep them, union them. And then here we would have
If we take a high-level perspective then in terms of what the results are, we can just look at the last line, right? What does that tell us about the results? So how can we compare these three techniques based only on that last line? Open to everybody.
so we reach error here.
Okay, so we found an error that doesn't exist if we use data flow analysis.
Here we reach the initial U,
Mm-hmm.
and here we reach U as well. So these two don't reach error, but this one causes error.
Okay, so that's in terms of how precise they are. So why would we want proper simulation versus path sensitivity?
Smaller.
They're not-
It's a lot smaller.
Smaller.
Yeah, exactly. Exactly. That's the whole point. That's everything.
Could the PSA be reduced? Because you could just, it has all the information to change it into process.
That's what
That's
Proposition is doing.
that's what this is doing. That's the point of this paper.
Yeah.
People didn't do that before.
Yeah, but they're doing it online, like as you move through. And this, at the end, they are, okay, yeah.
Oh, so if you do it after the fact, then you've already made all those paths.
Yeah, so it's kind of.
Yeah. That's the clever thing about it. If you do it as you go, then you refine things so that you don't have to compute those exponential paths.
Yeah.
Garbage collecting on the fly, so you can reuse that.
It's really good.
Reuse those resources.
I like that analogy.
So when we were very happy about the property simulation state that didn't reach the error state, and it was very dense compared to the extra information that PSA had, we reached a corner case. This is one problem with property simulation. Let's go through this example and see what happens. Why we have error here. So what happens here is that this is a simple part of the program, and this is the data flow graph for this program. And then should I go through it again?
Well, I think you can go through it at a higher level.
So maybe I can go through the merge part, that will happen. So here when
Well,
we
maybe describe what the snippet is doing, and then I think we can go through it at a high level, and we'll probably be able to get it.
what the code is doing.
Yeah.
So here we have flag, we assign the flag, but then we use it here. So first as the paper says, first the programmer introduces some variable, assigns some values to variables at different parts in the program, then later uses the variable.
With two different flags, right? That's the key here. We're checking two different flags for open and close.
The order of them matters too, doesn't it?
Not so much in this case.
So what happens here is that we lose information at the merge level for property states, because property states only takes the information if they are related to the to the property states from FSM. But because here dump and flag, we get the information here at this point, but at the merge point, you lose the information and go back to the UTOP state. And then here, when we want to check D to go to open, we might take, we would go from U to sorry, open. No, this is correct. Sorry. So we lose the information here, and then at this point, again, we check the condition, and then we add this information, and at this point, we check the flag. But before here, we lose the correlation between flag and the property states. So here, our options are from U, we can go to close, or from open, we can go to close, because we don't have the value for flag.
Yeah.
And then we reach the error state. While this is what PSA takes.
So is it clear that we're only keeping track of the facts of the program when we recognize a change in the underlying finite state machine? Okay. You have a question?
Is that a, they kind of say that this isn't a big issue because it doesn't happen. Is that true? Is this a big issue? Like it doesn't, it seems like you could avoid this, like you could get around it by
Yeah, I'm talking about it.
keeping track of more information.
You could, and we might want to ask a question about that. We in the royal sense there. Continue. We'll get right to that in a moment, I think.
So yeah, as we saw, property simulation loses information because of the correlation, because we don't save the correlation between variables that do not change the property state. And the justification is that property simulation matches the careful behavior of the programmer, and that was the programmer's fault.
So if we throw away this information, first thing we want to ask ourselves is, does that mean the system lies? Will it ever tell us that our program is correct when it isn't?
No.
Why?
If it so property simulation, it says that there is an error, there is an error.
But can we see why? But why?
So it's not the error.
Because
It's concerning.
Okay, but can we get the essence of that? So what is it equivalent to if you throw the information away?
That is one.
Yeah. It just makes it more over approximate. Throwing the information away doesn't make it under approximate. It just means that you start to merge more things and create a greater over approximation of the underlying system. So you'll get more false positives. You'll warn when you shouldn't.
But it'll still be correct.
Yeah.
This is another example that so same programmer just changed a very small change, and that issue doesn't happen here.
Mm-hmm.
Just by changing the order of dump open and flag.
Mm-hmm.
Here we have the correlation between D and F.
Yeah.
Here.
So maybe I misinterpreted your question earlier in terms of the order mattering. The order of if dump and if flag doesn't matter, which is how I interpreted your question.
Okay, yeah.
The order with respect to the setting of the flags does.
And the only situation where it kind of creates problems is when the flag is set prior to the.
Exactly.
these methods are being designed basically to find the error in the program. If the programmer was correct in the first place, then we don't even need this. You can also argue saying that instead of putting if flag, I can just put a dump and a close, then this problem never exists in the first place. So basically, the thing is that this might be a big problem, right?
It might create false positives.
Aren't they easy to find in like, there's only one case, and it's a fairly defined case where you've changed something that, you've set a flag that you close your file on. It's a fairly defined situation. Could you just search for that situation? Is that,
In theory, well, let's back up a second. Let's get to your other question that you asked before, because I think it's related. So if we look at these two examples and we consider them, they're both looking at the impact of over pruning, throwing away a little bit too much information, right? And the idea that, well, if we kept some of that information around, we would have been able to still throw away the things that were completely irrelevant, but still keep the things that were actually relevant. So with the claim that this technique is exactly the idea that you throw away the things that don't matter, isn't entirely true, right? You can throw away some things that do matter. In the name of efficiency, in the name of being easy to reason about locally. Do we have any techniques that would still be able to prune away all the things that definitely don't matter? And yet still keep the things that do? Yeah, slicing. That's exactly what slicing is. And if you look at some of the so-called sparse techniques for data flow analysis, that's what they do. They follow the use-step chains instead of explicitly following the control flow graph when doing data flow analyses to get exactly that optimization. Now, because you are dealing still with more information, you're not able to reason quite as locally, and there's still more to consider if you do that. So the fact that this is throwing things away and potentially introducing false positives will still give you efficiency advantages for that imprecision. It's a question of trade-offs.
And yeah. So now ESP uses property simulation to verify large programs such as GCC. The main insight is that different parts can be run with different level of precision and flow sensitivity. So actually, maybe this can relate to what you were talking about. So maybe we shouldn't always throw the information away.
It's possible.
Stateful values. Programmer provides FSM, also provides mapping from source code patterns to FSM transition and to stateful values creation. These two are the information that are given to ESP to the verification. Value flow analysis. First step is to discover which stateful values are affected at relevant function calls, and so it is usually flowing. The way they are doing it is flowing sensitive and context sensitive. They consider context sensitivity and flowing sensitivity.
In fact, they explicitly say that they do this using what technique? Slicing.
Yeah, I thought it was something. Sorry, I forgot the name of it. Slicing up? No, bottom up.
Backward slicing, whatever. I don't know.
You're so fond of slicing.
Well, it's getting to the essence of the problem, right? I mean, pointing out the relationships and the things that we've already seen is one of those cognitive goals that we should establish as part of the course.
Oh my God. I guess we missed the main part, which was the ESP, how ESP works actually.
So just based on what we've already seen, for those who've read the paper, can you think of an experiment that they might be leaving out based on the conversation we've had so far? They did one experiment showing how fast their system was in total.
experiment they
Yeah, they're leaving out some pretty obvious experiments, even with their limited analysis of GCC, which is all they did. So they looked at their system and how well it behaved using the property simulation. They didn't look at
Anybody else?
well, any other possibility at all. I mean, what if they just did slicing? How well would that behave? Would that be enough? Maybe if they do slicing, that gets rid of most of the things anyway, because most of GCC doesn't deal with files. It's tough to say. We don't know.
Isn't slicing a concept, not a technique?
It's a technique as well.
I have concern that they choose GCC for their case because GCC is not particularly known for being very file input output
Yeah, it's
bound.
a weak case study.
It's also not exactly known for having bugs.
Hmm?
Not known for having bugs.
This is not exactly true.
No, so we found, right?
Yeah.
GCC, the guys found 500 bugs, but they were not very file input output related.
Yeah.
That's the thing.
They're usually related to things like code generation, right? Generating meaningful code. I will say that this paper bears a striking resemblance to Project 2. I mean, you don't have to do with anything path sensitive, but they do have a delightful outline of how to do interprocedural analysis.
Sold this early. In that.
I could have.
Yeah.
He's giving us reading break here. That was the whole point.
I find it somewhat hilarious that this is all a shock to us. Nobody made the connection because nobody's like this haven't yet.
There's a high probability of that. Yeah, yeah. I did the same thing in my undergrad course this semester where I explicitly tell the students to do the project before the deadline because there will be problems. And yet I get, emails
Was
an hour before the
276?
deadline. Yeah, 276.
Was that yesterday?
That was yesterday.
In class? Actually, no one asked questions in class.
Hmm?
No one asked questions in class, did they? About the project.
Easy in your
I do a little bit better at drawing questions out of it. I got one. Yeah, undergrads in the 200 level, not so much on asking questions. I definitely recommend looking at that. In this last few minutes we don't have, though, I also want to make another point. Pointers are an issue here.
Alias.
Yeah.
Alias analysis.
Yeah, pointers are a huge issue here, a huge issue. Because if you're doing these state transitions based on, the abstract state of something, you have to know what that something is. If you have a pointer that can point to two different, let's say, mutexes for some random reason, which maybe isn't clear until you read the project, then you have to be able to differentiate those. And when somebody asks about the subtleties involved with that, I'll answer about the thing you don't have to do, which ties into one paragraph exactly in his paper. That you don't have to handle, so that's a good thing. But it's something in general you would have to handle. So
which paragraph was that?
well, there's this property simulation thing which talks about the alias sets. So let's hypothetically say you've got a pointer, and it could point to one set of things, or it could point to another set of things. Well, you've got to handle the possibility of one of these sets being modified, but maybe that set wasn't modified. Maybe a different set of things was modified. So there's this divergence based on the May alias analysis, based on, well, this pointer could point to different things, where you have to ask yourself, well, okay, if it pointed to this thing, then that means that thing got locked. If it pointed to something else, then that thing didn't get locked. And so both possibilities exist.
I assume you would have to take, if you can't reason about which possibility you took, you just take the conservative method and say, well, either one of them could have happened. So,
Yeah. And what does that do? Well, it adds false positives. Because you have to say, okay, I'll continue on saying this could be locked or unlocked, and the other thing could be locked or unlocked.
okay. I'm assuming that the thing that we don't have have to do in the project is conservatively say that you don't have to.
I wouldn't say conservatively, because that would be the safe situation. I will say that you will have to recognize the flow of pointers through functions, because that's what a mutex is, right? So if I give you a mutex as an argument, you're going to need to be able to tell what that was, but you don't have to handle these weird cases of, well, this pointer could point to two different things, so I need to handle locking and unlocking for both of them. I'll let you say, okay, it can point to two different things, and so I'll under approximate and say, whatever happened to both, which is not safe,
Oh,
but it's easier.
alright.
As long as it's easy, I'm happy. That's it.
Okay. Okay.
I think I like that option. Sounds.
I imagine there'll be some questions about that once you understand what I just said.
Come on, we are graduate students, we are researchers. We like.
Okay, so I imagine there'll be some questions right before the deadline. You'll understand what I just said.